Hello, my name is Bruce Neubauer. I want to speak to you, my students, for a few minutes about what I call computer and network architecture. I'm not using that word architecture in exactly the same sense that computer scientists use it, but nevertheless, what I want to speak about is about the design of individual computers and networks of computers. Let me begin with an evolution of computers. In about the 1960s, companies like IBM and others were building and selling very large computers called mainframe computers. These were costly, on the order of perhaps $1 million a piece. They were large, they were difficult to maintain. We still have mainframe computers. The next step forward from the mainframes were called mini computers. A mini computer is on the order of the size of a refrigerator. So by modern standards, it's hardly small, but compared to the mainframes that it followed, it was small, so they called it a mini computer. And again, we still have mini computers. These are called legacy systems or legacy hardware. Many of these machines run programming languages that are no longer popular today, like COBOL, but they're still in service, they still work, they're still valuable, and many organizations are very, very reluctant to let go of these legacy systems that often run in what is referred to as the back office or the back end of a network. In about the 1980s, companies began building microcomputers, and we still use microcomputers. Microcomputers include desktop computers, towers, laptops, and now, of course, we increasingly are using mobile devices, which are also computers, things like the iPad, the various kinds of Android, the various kinds of tablets that run Android operating system, smartphones, and so forth. So what we observe over time is that computers are becoming smaller, they're becoming less costly, they're tending in the direction of becoming wireless as opposed to connected together into wired networks. And all of this is this trend towards smallness and increased power and reduced cost is all made possible by something called Moore's Law, which is the fact that approximately every 18 months, scientists discover ways to pack more of everything into hardware. Technically, it's about transistors on a chip, but from a managerial sense, it's that about every 18 months, you can buy a computer that is twice as good as the one you bought 18 months ago for about the same price. So, let me speak for a few minutes now about an individual computer, be it a mainframe, a mini, a micro, or even a mobile device. A computer contains or includes hardware, an operating system, and applications at minimum. Hardware is the physical thing. I don't believe that we're ever going to get to the place where computers will be entirely virtual. There will always have some physical being. Operating system is a layer of software instructions that runs on the hardware and talks to the hardware And applications are yet another kind of software that allows humans to do things. And the applications run on the operating system, and the operating system runs on the hardware. An example of an operating system, for example, is Windows or Linux or Mac OS X, Lion, Snow Leopard, and all the rest. Unix on a mainframe computer. Examples of applications are things like Microsoft Word. Now, the beauty of this layered architecture is that it allows programmers who write applications not to have to think about the hardware that the application must run on, because there's an additional layer between the application and the hardware. The people who write applications, the programmers, write their applications to run on a particular operating system. And as long as the application can talk to the operating system, and the operating system can talk to the hardware, then the application can run on that hardware. The combination of hardware and operating system is called a platform. For example, Wintel is a reference to a Windows operating system running on hardware including an Intel processor. Now, it's possible for there to be virtual operating systems. In this case, there is an operating system that runs on the hardware, but then there is another operating system running above the operating system that runs on the hardware, and the applications talk to the virtual operating system that talks to the operating system that talks to the hardware. For example, some companies like Apple hardware, but they also like Windows operating system because they want to run Windows applications. Well, it's possible to run Mac hardware. The physical computer is a Macintosh, Apple, but it has to have, of course, the Apple operating system to talk to that hardware. But then it is possible for, say, Windows XP, Windows 7, whatever, to run on top of the Mac operating system as a virtual operating system, and then for the Windows applications to run on the virtual operating system. This slows things down a bit because there's an extra layer of translation, if you will, in the stack, but it's possible and it's not unusual. Now, the word Java has multiple meanings in the context of computer systems. Java is kind of like a virtual operating system. That's one meaning of it. Java is also a programming language, and JavaScript is yet another programming language which regrettably simply has the word Java in the name but is not the same programming language as Java. At the moment I'm speaking of Java, the thing that kind of looks like a virtual operating system. Programmers can write applications that target not an operating system, but rather Java. Java can